Um, so we have a very special session this morning. I am really excited about this. The panelists that you're going to hear from are rock stars within the industry, and it's on a subject and topic that is extremely important. And I think this will be something very significant. I want to introduce each of the panelists one at a time, and that will come up. And during this panel discussion, I'll also be going out there to you. If you have any questions you'll want to ask the panelists. So that will be coming up. Our first panelist is Rory Bolt, who joined Kioxia America in 2017. He founded and built teams, delivered products at 4 storage startups that had all successful exits. Corey has more than 25 years of experience in the data storage system business, including diversity into areas of data protection, high performance computing, the HPC space, and he had 10 years as VP of software engineering at Samsung, technical director, CTO counsel at NetApp. He was CTO counsel at EMC, and vice president, chief storage architect, distinguished fellow at Quantum. Rory has been granted over 12 storage-related patents and has several pending. He has a Bachelor of Computer Science degree from UCSD, University of California, San Diego. Come on up, Rory. Have a seat with our panel here. Second person I'd like to introduce is Niket Agarwal, distinguished engineer at NVIDIA, working on the DGX cloud system architecture and full stack optimization across data and AI infrastructure. Before working on DGX Cloud, Niket worked on building Omniverse Cloud, a managed software as a service running on Azure and being used by customers for digital twin simulations. Niket has spent 1.5 decades working on large-scale AI and cloud distributed systems. He has a PhD in computer architecture from Princeton University and Bachelor in Technology and Computer Science from IIT Kharagpur. Come on up, Niket, join us. Thank you. The third panelist is Paul Cho, who's a corporate EVP of Products and Solutions Planning at Samsung Semiconductor. He leads product roadmap and technical collaboration discussions with U.S. customers and partners. He's often involved in driving strategic initiatives and delivering new types of synergistic solutions that build on Samsung's silicon products and technologies. Paul has also contributed to developing multiple generations of server-class storage systems at Samsung. He holds a PhD in computer science from University of Minnesota, Bachelor in Computer Science from Seoul National University. He's a tenured faculty at University of Pittsburgh and a fellow of IEEE. Come on up, Paul. Join us. You can applaud for all of these people. As soon as I finish all the introductions of everybody up here, the next panelist we have is Patrick Chow, Senior Director of Storage Product Management for Supermicro, and oversees both the NVMe all-flash and the 3.5-inch HDD storage product lines. He has more than 20 years of experience in NAND flash storage, servers, and software product design, product management, business development in the IT industry. Patrick earned his master's degree in computer science from NYU. Come on up. Patrick, thank you. Next we have Niloy Bhattacharya, who is Director of AI Solutions for Vast Data. Vast has really revolutionized the storage industry with AI data pipelines for customers as a part of their architecture. With over 20 years in the hardware and software industry, he excels in product strategy and driving enterprise transformation. Niloy has led teams to achieve significant growth, including taking VCE from $0 to over $1 billion in annual sales within 4 years. And his leadership includes EMC and Dell, and focused on understanding customer needs and fostering team types of transformations. Coming up, Niloy. Oh, already here? Thank you. You're fast. And last but not least, leading our panel is Rob Davis, Vice President, Storage Technology at NVIDIA, and he focuses on ways to apply high-speed interfaces such as 40G, 100G to storage systems. Over the last 2 years, he's moved NVIDIA into a leadership position in NVMe over Fabrics, and as a technology leader with visionary, unbelievable for over 35 years. His background, he was VP and Chief Technology Officer at QLogic, where he drove their development and marketing of everything from fiber channel, Ethernet, InfiniBand, a full networking portfolio of products. He also, before joining QLogic, worked at Ancor Communications, which was a leader in fiber channel fabric switch technologies. And his expertise includes virtualization, all the different protocols of data storage technologies. Rob, come on up. Thank you.
Thank you, Jay.
Could we have a round of applause for this panel? Thank you. And with that, I'm going to turn it over to Rob. And
Thanks again, Jay. Good morning, everyone. So, on this panel, we have an expert in AI memory, an expert in AI SSDs, an expert in AI storage systems, an expert in building AI storage systems and AI servers, and then an expert in how to actually use it with AI software. So I think you'll agree that we have put together a panel that hopefully can answer any questions you might have. But to help you out, we're going to start off with each panelist talking about a particular challenge they see in either memory or storage or both when you apply AI applications to it. And kicking that off will be Rory from Kioxia.
Thank you, Rob.
If the clicker worked.
That's there.
Wow.
Could we get some help with the first slide?
It's advancing on the left, but not on the right.
This is so classic.
Oh, there you go.
There you go.
Fabulous. So I'm going to start off with a little bit of humor here. The title to this slide is actually an unattributed quote that I heard someone say at the File System and Storage Technologies conference earlier this week. They claimed AI doesn't have a storage problem. And the original version of this slide had the retort, it has all the problems, but legal came in and toned that down a little bit. So
Legal will do that.
Little insight to my humor there. And when I say it has many storage problems, it's because there are many facets to the AI workload and work streams. And so depending on what you're doing, whether it's in the data center training or doing data center inferencing or out in the edge with PCs or wearable devices, you face different challenges. And it's pretty much all the classic storage challenges. There can be needs for extreme bandwidth, extreme low latencies, capacity of the devices, power budgets. I'm not going to name any names, but one of these chairs works for a company that consumes a lot of power. And finally, just density.
Actually, two of these chairs.
Okay, two. There
We're
we
even
go.
consuming chairs.
So what this means is that there are different demands on storage, and with few exceptions, people are using shared storage in their environments. And so you get an I/O blender effect on the endpoints that see large sequential streams and a bunch of small reads coming in, and it can be very, very challenging. So we don't see any specific differences in a general sense with AI environments, with one notable exception, and that's when the GPUs are directly interfacing with our devices, okay? And the thing that's unusual there is a direct result of the architecture of the GPUs themselves. Most traditional servers, a couple hundred cores, we see queue depths in the hundreds, right? You get a nice GPU that might have 10,000 cores, and suddenly we're seeing queue depths that are in the 10,000 range, and this is only increasing. So this problem's only get bigger, and we are focusing on ways that we can make our devices perform better in these environments with extreme number of queues and extreme queue depths, okay? And then the other thing that I'll say is sort of a general comment about storage in AI is there appears to be indications that the actual read-write mix may be different from traditional storage environments. Classic storage environments, we see sort of a 60-40 or 70-30 ratio favoring reads over writes. And early indications are that in the AI solution set space, it may be closer to 50-50 between reads and writes. That might be influenced by very high write workloads on the ingestion side, where you're scouring or collecting very large data sets and then preconditioning them before you do your training. Checkpointing may contribute some amount to that also. We're not really sure yet. We're still investigating these causes. But in general, we see many, many different facets to the storage problem. And what we personally are focusing on today are retrieval augmented generation systems. We see this as a growth vector for storage because it allows enterprises to leverage these large language models that have been created at great expense and use them on their private in-house data. And they do this by vectorizing their data to create embeddings and vector databases that can be used to feed the prompts into the large language models to improve the timeliness of the information presented, as well as the accuracy of the results. And so we're doing a lot of work at Kioxia in ways to enable scaling of these vector databases and remove sort of the memory wall limitations that we see. And by doing that, we can reduce the overall system costs while still providing good performance in these systems. And I think it's a very, very fertile ground for storage applications. Okay.
Thank you, Rory. Nick?
Cool. Awesome. So yeah, great setup from Rory for stuff I want to talk about. So Rory talked about a lot of the storage and memory problems. There are many of them that applications are facing. I wanted to share some numbers to put it in perspective of how things are kind of evolving. I'll focus on training first. So if you look at large language training, it's breaking storage systems in many dimensions. So if you look at checkpoints, for example, contrary to like traditional workloads, like this is a very massive throughput workload. So if you take like a modern 2 trillion parameter LLM model, the checkpoints there can be in the range of 30 terabytes. And the way the reads and writes works is there's like tens of thousands of GPUs trying to load them concurrently during a read of a checkpoint, and the GPUs are idle when this is happening. So let's say it's a 30 terabyte order 30 terabyte checkpoint, then we want to load from distributed storage, and you have a terabytes a second of bandwidth, right? So that's a lot of bandwidth from a distributed file system. It will take 30 seconds for that checkpoint to load. And all these 30 seconds, the GPUs are waiting, doing nothing because you're waiting for the checkpoint. So optimizing that throughput is very important for GPU efficiency. Similarly, when we do writes, all these 30 terabytes are going to be written by tens of thousands of GPUs at the same time. So it's a thundering herd problem for storage systems. So pretty unique characteristics that distributed storage systems are facing when we're designing these workloads. So something to kind of scale for everyone. Similarly, on the data loading side, what we're seeing is, so everyone's done training their text-based models, right? So you have a new one come out every week. They're growing in kind of dimension. But most of the modern training is now moving to multimodal, so images and now videos. And videos are a great form of learning, and humans learn much better through videos as well, right? So we're seeing early results that translates to LLMs as well. So videos really help us understand the world. But the video models are very different when you look at like data ingestion for training. So just to give you some perspective, like if you train like a big model like a Llama or GPT-4, even like 15 trillion tokens is what modern LLMs are pre-trained on. That's double-digit terabytes of data across many, many months. So you're ingesting like, let's say like, I don't know, like 20 terabytes of data over 3 to 6 months. That's nothing for storage read throughput, right? But when we go to video, the data is kind of going into tens of petabytes, and sky's the limit. Like people are generating videos every day. We'll generate one for this panel as well, and hopefully AI will learn something out of this video as well. So we're seeing storage capacity becoming a big bottleneck in terms of data ingestion. So tens of petabytes, and moreover, even storage throughput and read latency is very important for large scale video training. So I wanted to kind of show some numbers that we're seeing is like just a 30-second clip of data is 5 gigabyte of uncompressed data that the GPU needs to read, right? And imagine learning from like billions of hours of videos, how much read of storage we need to do, right? So the entire system from the GPU up to the storage system, this entire data path needs to be designed for this massive data ingestion going forward. So that's on the training side. Seeing a lot of storage and interesting memory problems on the inference side as well. The chart on the right, we wanted to show typical kind of memory usage for modern LLMs. So the chart, what it shows is x-axis is the sequence length. So when we go to something like ChatGPT or Gemini and we talk to it, there's this concept of context. So we enter a bunch of text, that's the context, then it replies, then we enter more text, then it gets appended into the input to the LLM, and the input sequence keeps on growing as we keep talking to these LLMs, right? And the way these modern LLMs work is to give you the next token, you need to read the entire context of what we've been talking to it about. So this whole concept is what's called like KV or key and value. It goes into the transformer model. So modern LLMs cache it. So we have something called a KV cache that's really important to get LLMs to perform. And the y-axis is showing as we keep talking to our LLM, how does the memory requirement grow? And as you can see, like a H100 is about 80 gigabytes of memory. And if you take something like a GPT-3 model, you keep talking to it after 32K input sequence size, you run out of memory, right? So how do you solve it? You either shard the model across many GPUs, in which case you're using GPUs for memory, right? Not a great use of those GPUs. The alternate axis where a lot of people are trying is using like offloading or hierarchical memory. That's where a lot of innovation is, can happen, is can we offload that memory to, let's say, the CPU memory pool, right? The thing that doesn't work naively in that architecture is all these LLM applications are memory bandwidth bound. So this next token prediction for inference is completely memory bandwidth bound, right? And we went from a terabytes a second of HBM bandwidth to PCIe, which is a 50 gigabytes a second memory bandwidth interface, right? And it's not coherent, it's not efficient. So you break down this, like we haven't enabled this offloading architecture at the hardware layer, right? So lots of folks are thinking about it. NVIDIA's been thinking about it so deeply. So the table on the right shows the CPU offload bandwidth of a traditional architecture like a Hopper or a Blackwell GPU. You're still limited by PCI Gen 5 bandwidth, but we've architected the system called Grace Blackwell or GB200, where you get way faster CPU to GPU, CPU memory to GPU bandwidth, right? So it's 450 gigabytes a second, so an order of magnitude more than PCIe. So it helps us kind of innovate in this offloading area, which is the bottleneck for modern LLMs, right? The next step would be, okay, we'll run out of CPU memory, right? It's limited, then how do you go to the storage layer? Then let's think about the kind of interfaces there and bandwidth and latency kind of properties, right? So a very exciting area for this kind of group to work on. And last but not the least, I think Rory talked about RAGs. That's also breaking traditional systems a lot. People are ingesting like billions of documents. All these embeddings are like really big. So they run into memory limits. We've started ingesting videos now, so video embeddings will be much larger. So all this work is just starting, and yeah, really looking forward to what the industry can do here.
So Naket brought up a lot of memory problems for you, Paul.
So we'll solve those memory problems based on 5 pillars that I'm going to capture right now. So when it comes to AI workloads, it's all about bandwidth from my viewpoint. That's the first thing. And indeed, HBM stands for high bandwidth memory. And if you go to Korea or Boise, Idaho, moms are talking about HBMs today. It's the hottest product on the market. We are talking about 1 terabyte per second bandwidth out of a single HBM cube, and we are looking at 2 terabytes per second or even higher bandwidth in the era of HBM4 and 4 Echo. Of course, higher bandwidth could translate into higher power, which nobody likes. We saw the trajectory of hitting more than 50 watt per cube if we continue our current design methodology. So the innovation we brought to the market is to introduce an advanced logic process within HBM. So in the case of Samsung, we decided to introduce 4 nanometer logic technology to use in the base die of an HBM4 and 4 Echo. With many innovations in the memory cell technologies design and also logic process and logic design and packaging, we are suppressing the power consumption to about the same as previous generations, well within the power and thermal limit. Capacity is important. There's unsatiable demand in capacity in the memory and storage. And we are trying to improve the density of HBM, but if you look at XY dimension, the lateral plane, we could achieve 2x, 1.5x, moving forward 1.3x. That's still limited. So we look at Z direction, and we are talking about stacking 8 dies, the memory cell dies, 12 dies, then eventually 16 dies in the HBM4 Echo time frame. And it is impossible to overestimate the importance of RAS in this domain. You are running your workloads 24 hours a day at the peak rate, and memory is not the exception. We have to improve the RAS, and this is not only the memory problem, it's a cross technology, cross-component problem where we need to have this system level viewpoint on improving the reliability, availability, and serviceability of memory products now. And lastly, and not leastly, customization. There's this big notion of customization in the domain of AI memory, and that's going to only help the bandwidth aspect, power aspect, capacity aspect, and finally RAS aspect, all through customization. And this requires a lot of innovations in memory technology, design technology, and base die design, and overall integration using advanced packaging. And we at Samsung are trying to make this happen by combining all those things together.
Thank you very much, Paul. So Patrick, how are you going to package all this?
Yes, I see in the previous, they already mentioned all the AI challenge. But for Supermicro, we are engaging our customer the large-scale data, AI data centers. We can summarize our AI challenging as these 4 main categories. The first one is the growing data set. I think the previous as mentioned, no matter the data size or the parameters continue growing. And if you have the storage, you can solve today's problem. It's not enough because your data, your parameter will continue growing. So no matter you are leveraging the scale out or scale up solutions, you need to think about the futures. How could you expand your storage? The second one, just like Roy mentioned, mixed workload. Right now, the data pipeline is much, much more complicated than the before, right? From the data ingestions, that is a loss of the sequential write, and the data preparation, they have the mixed workload. Going to the training, you will have the checkpoint that you need to kind of high performance sequential write, and you load back the data that is random the read. And then eventually you will have the model being built. You will use the inference. That is real time. You want to do the inference and serve your customer. So this workload is totally mixed. Previously, traditionally, you can use one size of the storage media or the storage system to cover that. But right now, the new LLM data centers, you need to design a different, unique storage system and the software total solution to solve this problem. The third one, we talk about the performance, right? And we have the study and found out the storage inside the AI data center maybe only occupied roughly 10% or less than the budget. But I/O weight associated elements in the whole training process could be reached more than 40%. If you don't design the system correctly, your $1 billion GPU cluster is waiting for you reload the data to do the checkpoint. Your GPU investment is idle. So how did you design the right systems, accommodate with the right storage medias, and also the storage software? You can keep your GPU continuous works and provide the best performance. The first one is the high power consumption. I think everyone knows right now the CPU, GPU consume more and more powers. Not only for the single systems, single chassis, and we are suffering how to design and cool down the system. Supermicro have the leading DLC, direct liquid cooling, to cool down the GPU systems. On the storage side, it's not yet, but we are foresee we are also continue to kind of have the new cooling technologies. But how about the data center side? We are working with large-scale customer on data center. Each data center, their power budget is limited. The cooling budget is limited. Their priority is to allocate the power and the cooling budget to the GPU farm. And they reserve a very minimum power and the cooling capacity for our storage systems. So that's why we will have the new higher density, higher capacity flash or DRAM, or we leverage the new technology on the software. You do the different technology to solve the compact storage and reduce the footprint in order to feed into your data centers. And with all these 4 different challenges, we need to be carefully working with our partners, working with our customers to design the new generations storage solutions in order to control your TCO or TCA. So from our point of view, Supermicro will provide purpose-built storage solutions, no matter you are continue using the U.2 or you are leveraging the latest, greatest, the EDSF new form factors. You can use the TLC, you can use the QLC, or the new SCM technologies, or any others offload engines, and in order to provide our customer the new AI data centers a brand new solution to solve all the problems. Thank you, Rob.
Great. Niloy, how are you going to put all this together
Well,
and provide a system to fit these challenges?
Well, that's exactly it, right? I think Patrick provided a great summary of the inter-data center challenge, right? You only have so much power, you only have so much real estate, cooling, bandwidth, all of these challenges you have to sort of rationalize and deal with. And then, of course, as you get onto the inference and the model serving side, you're then also dealing with latency and distribution of workload. So as we've been working with our customers, this inevitability of needing to distribute both model training as well as inference workloads across multiple data centers has become a reality, right? This is something that's not just, oh, I wish I could. This is something that I have to do in order to get past the boundaries that I'm reaching within a data center. And I think at the very beginning, we did a good job of saying that the intra-data center challenge that we're facing has to be overcome with this ability to shift a large volume of data, right? Nikit kind of pointed out how big these data sets are, right? Especially when you start getting to video. So simply replicating that data across all of these data centers that you want to distribute your workloads around is a virtual impossibility, right? We hear this from every customer that we work with. And so one of the areas that VAST has been working with our customers around is this concept of a data space, right? Making it so that at the metadata layer, we can synchronize a large number of data centers and share the identity and information, the metadata, about the data that's being stored. This enables you, once the GPU demand is there for a particular workload, to retrieve that data in semi-real time, right? There's prefetching and there's some other algorithms that are in place that will help you retrieve that data so that you have the particular portion of the data set that you want to work with without needing to preordain it, right? If you had to come up with a scheme that said, oh, before I can kick off a training job, I have to move exactly these files or these objects, it would become very cumbersome, very arduous, right? So being able to, at a metadata layer, share all of the information about the data set, prefetch the components that are needed for the job, but then also at the metadata layer, do something called write leasing. So that when you need to write data to this common namespace that you're dealing with, you now have the ability to lease a portion of that for the writes that you need to do. So once again, at a metadata layer, everyone becomes aware, okay, so the latest piece of information about these particular, what we call elements, is located in this particular data center. And so between the prefetching and the read caching, as well as the write leasing, we are now essentially able to, while not eliminate the problem of data gravity, we're certainly able to make it much more seamless to distribute your workload across these data centers, which, once again, especially when it comes to inference workloads, where latency is a factor, right? Imagine if you had a vector database that you were referencing as a part of an inference workload, and you had to either replicate it in its entirety or pre-plan and pre-shard various components to various locations. It would become a huge challenge, right, operationally. And so that's one of the things that we've been working on with our customers and with our partners on stage here to really sort of make that portion of distributing your data set across multiple data centers a lot easier for our customers.
Awesome. All right. Now we're open for questions.
Okay, I have a microphone here. Anyone raise your hand if you have a question? I'll bring the mic over. While you're thinking about your questions, I just received one over here that was for Rob, you or Nikit. The question was, what is an ideal storage fabric for training?
Nikit?
Yeah, so I guess ideal is a big word, right? So we know what we know, right, for current workload. So if we were focused on text-based LLMs, I give you some numbers, right? So everyone's been training text-based models for the last couple of years, right? And the throughput there is megabytes a second across the entire data center, right? Except when you do checkpoint reads. So I would say like, yeah, USB drive is an ideal storage system for LLM-based text training. But things evolve, so we have to look at the future. So things that we do see kind of captured in terms of numbers in the slide is you do need really high throughput, and not just reads, writes as well. A lot of storage systems don't optimize for writes. But what we end up seeing is, let's say you have a large LLM training, so you buy 100,000 GPUs, that's what a lot of people are doing right now, right? So that cluster, it's running, let's say 80,000 GPUs, large LLM training, it wants to do a huge checkpoint write. We need to support that write while the other 20,000 GPUs are doing inference or other workloads on that system as well, right? So mixed workloads with a lot of high throughput reads and writes is definitely required. Something that not all storage systems have traditionally supported, and couple that with like hundreds of petabytes of storage capacity, right? So everything's growing. But I wanted to kind of also share one challenge we see as we talk to a lot of customers. So we help a lot of customers build reference architectures and deploy them. So I think you touched upon the power problem, right? So let's say I told you to build this 100 petabyte storage system with 5 terabytes a second of read-write throughput. You can build it, but it has to be in the same data center as the GPUs, and end up consuming 40% of the power of the GPUs. That means we can put 40% less GPUs in the data center, right? So we have to be very clever about how much power we are taking from the fixed data centers while meeting these requirements. That's where a lot of the tiering architectures also come in. And I want to pitch out like it's not a hardware problem only, it's not a storage software problem only, it's a co-design problem. So we should work with the models, with the frameworks, so we also tiering things the right way. I think I love how you put in the vast work is like you can prefetch stuff, right? So data, let's say this 100 petabyte can be somewhere, but if you can prefetch, right, you can apply AI to teach you when that video is going to be required for training or inference, and we can prefetch it at the right way. That's the ideal storage architecture, right? It has to be co-designed with the workloads themselves.
Anybody want to add to that? All good?
Okay, next
You said
question.
it well.
Thanks, Jay. Hello, I'm Chuck Sobey, General Chair of FMS. Thank you all for being here, and certainly thank you folks. We're really learning a lot. This session came about from being in Jensen Huang's keynote at GTC this year. He said that we're going to have search is going to change. Instead of retrieving data, we're going to create the data as the basis of that. And that just lit my head up. I thought, this is going to change everything. So I started talking with Rob here and said, what is that going to look like? And how can we at FMS support that? So how does it change, and what are a couple of things we need to do next year to support this here? What new tracks do we need?
I think Niket actually pointed out a couple of the changes in the behavior that we see, especially as we get into these large retrieval augmented flows, right? And retrieval augmentation across many different modes of data, right? If you think about it, you're in an enterprise use case, you ask a question, you're absolutely right? It's not a matter of, hey, here are your 5 documents that most closely relate to the question you asked. It's getting to a point where AI can generatively prepare a response based on those references, right? So I think that the trends that we need to look for and sort of the tracks and the conversation really comes down to how do we deal across these massive scales of information. I think as all the colleagues on the panel stated, you're going to hit memory limits, you're going to hit bandwidth limits, you're going to have to come up with not just tiering, but more intelligent ways to retrieve and store and work with this data. And so, you know, I guess the really cool part about being in this industry and working with our customers is seeing that innovation and really, you know, approaching it systematically, right? From the software, the application software, to the infrastructure software, to the hardware, to the data center architectures. And I think it's going to be a lot more of that, really kind of honing in on, let's take retrieval augmentation. What are the specific enhancements that are needed in the retrieval augmentation space? What are enhancements that are needed in training space or preparation, right? One of the things about video-based inference is all of the work that goes in to preparing files, right? Image files are very large, and generally speaking, the areas of interest sit in a subset of that, right? So all of the work that goes into data preparation, so I think those are all areas that have a bunch more innovation in front of us.
So Rory, you said you guys were looking at Kyokusei areas that you could maybe offload or accelerate some of those things that we're talking about now from a RAG perspective. Did you want to elaborate on any of that?
Absolutely. So, in my experience, the really large advances in computing occur with algorithmic changes. It's not incremental doubling the bandwidth of something. It's fundamentally doing things a different way. And we have a number of different research projects underway in this area. In the keynote speech we gave on, was it just
2 days ago.
Tuesday, 2 days ago, losing track of time here. We were highlighting a technology called Isaac, which is leveraging some fundamental research that was performed by another company, Microsoft, around changing vector databases and the representation of the data, quantizing the data to allow more efficient processing of the data. And once again, it's a technique to get around these memory scale problems. So that's work that's being done today. Longer term, we have a fairly advanced program of offload accelerators that we're undertaking. Once again, this is research at this point and proof of concept work. And it's not without its challenges. I mean, one of the great things about this area is it's rapidly evolving. And so,
who even knew what RAG was
Right.
4 months ago, you know?
And so when you think about trying to plan for hardware accelerators, offload engines that take years to come into a mass production, you have to focus on fundamentals that are highly unlikely to change and really sort of narrow the scope there. But I'm looking forward to great advances. And once again, I think the key is looking at the problem in a different light and changing the algorithms.
Paul, did you have something to add to that?
Oh yeah, but to realize the vision that we could generate and create data instead of moving all those existing data or results to somewhere, I think fundamentally the problem is how to improve the useful compute under power constraints. It's at the card level, it's at the server level, it's at the rack level, and finally data center level. This power problem is such fundamental that we need to improve the useful work that we could achieve with the power constraint. And from my viewpoint, the highest traffic happens between GPU and memory. So that's where we really need to make innovations into and improve that power efficiency.
Gotcha. Patrick, you think about power a lot.
Oh, yes. I think maybe 10 years ago, everyone is talking about the software-defined storage, and that they can put the software or operating system on any kind of a commodity servers. Right? It works until the AI shows up. Right? We just solved the training problem, the high capacity, high density. Suddenly, as you say, the rack is coming. We need to have offload. We need to have all the new components come from all the industry leaders. And then we need to figure out, as a system builder, we still have the limited capacity, cooling, and even the space. How do we design these systems? You want more memory? Unfortunately, I can only do 2 things per channel, right? And the space is a limit. So how do we work together and design a purpose-built new AI storage system with the industry leader from software, from the component, or even from the NVIDIA, right? You guys are fundamentally driving the AI. That is the key, and the Supermicro is continue working with closely with the partner to purpose build and design the AI-ready storage for everyone.
Yeah, I think you guys have specifically focused in on the cooling aspect as well, which, to your point about usable compute per unit of power, you know, any sort of waste that we have to remove from the equation, right? Sure. And so that's where I think, you know, both NVIDIA and Supermicro, a lot of the innovation around liquid cooling kind of speaks to, you know, doesn't matter whether it's even 10% more efficient to do liquid cooling. The fact that it's 10% more efficient is very material when you're talking about these types of workloads.
Yeah.
Especially at data center scale.
Yes.
Yes.
Right. And sustainability is a hot topic in this industry for many, many reasons, and we're all working towards greater power efficiencies. Absolutely.
Okay, I've got one here for Niloy, and it really relates to everyone on the stage. At VAST, you have this platform for storage for AI-related workloads, and you have direct touch to a lot of customers. What are you asking of the people on this stage based on those customer needs?
Yeah, I think a lot of it was frankly already mentioned, right? Density at performance is always a part of the equation, right? At a point in time, to your point about the historical, you know, people got into a motion around optimizing around density, and performance wasn't as important, right? And what AI has taught us is density at performance matters, right? I think the other vector that was talked about earlier was performance and density per watt of power, right? That's another big thing, and you know, because we get to this point where, as from a storage software standpoint, everything we can do to minimize our footprint is critical, right? Because every rack every watt of power you're having to use is taking away from, you know, regardless of how efficient the GPUs are or become, you still want to be able to process more net workload, right? And so, yeah, those are the sort of the two key things is efficiency around power and really being able to deliver performance alongside density.
Very good. Anybody have something to add to that?
I would just add, in terms of interconnect and networking, you know, we're also doing fundamental research into optical transports, and believe that there will come a day when you won't see quite so many copper traces between components, right? Yeah. So an immense amount of power is used in just moving the data, and as the frequencies get higher, the problem becomes cubed.
Light doesn't take electrons, right? So
Yep.
no heat.
It's also a cost factor that ends up playing into that.
But as the speeds get faster, you know, we have 800 gig coming.
Yeah.
And
Oh, yeah.
As you all know, that the cable length, you know, in my career has kept getting shorter.
Are there any other questions? Can we have a round of applause for this panel? Thank you so much. Thank you all for coming to this session, and they'll be available on the stage if you have any questions one-on-one you'd like to ask them. Thank you very much.
Thank you.
Awesome.
Thank you. Yeah, thank you. Nice talk. Yeah.
Rory.